In this problem, we know the following terms. We know R naught, which is the initial height of the meteor. We know RE, which will be the final height of the meteor in terms of from the center of the Earth. So this is going to be considered the radius of the Earth because that's where the meteor is going to land at a height of the Earth's radius from the Earth's center. And then we'll go ahead and say we know the mass of the meteor, the mass of the Earth, and the gravitational constant. So the first thing we want to do is just find a work function that relates these terms together. And the one that I uh, think is most useful is the basic definition of work. And I'll just say S is some sort of distance that a meter goes. So let's go ahead and define some terms here. Here's the center of the Earth. Here's where the meteor is. We'll call this R naught. And the placement of the meteor in some term R is given by the center of the Earth to where the meteor is at this point. And at the same time, that placement of the meteor in terms of the distance that it travels can be considered S. So you could say that R plus S is equal to R naught. That's the distance that the meteor will travel. S is the distance that the meteor will travel from its initial position. And R is the distance the meteor is from the center of the Earth. And this is just going to be useful based on the equations that I use. So the force of gravity for objects that are very far from the surface of the Earth is going to be G M meteor, M Earth, divided by R squared ds. Now the reason these two are different is because this R depends on how far from the center of the Earth that the meteor is at a certain point. But ds is a distance that the meteor travels, an infinitesimal distance that the meteor travels from the beginning. So we kind of have two variables here that we need to reconcile before moving on. And in terms of ds, we'll see that the meteor goes from two locations. Actually, in terms of dr, for example, the meteor will go from R naught to RE. So now the only objective is to try to get this in terms of dr. And in order to do that, we're going to implement what we show here in this picture. So we're going to say that R is equal to R naught minus S. And that happens to be true. Since R plus S is equal to R naught, then R is equal to R naught minus S. So therefore, dr, which is what we want, is going to equal to dr naught minus ds. R naught is a constant, so there is no infinitesimal change happening there. So dr is equal to negative ds, and therefore ds is equal to negative dr. So now we can write that down in our equation. W is from R naught to RE, G M sub M, M sub E over R squared, and then dr, and there's a negative out in front. So now what I did is I replaced ds with negative dr, okay? The negative comes out in front. Let's go ahead and simplify this now. W is then equal to negative. G, M, and M, these are all constants, so there's no integration. So I'll bring this out in front. And we regard ourselves a proper integration now. The integral of r to the negative 2 is going to be r to the negative first power divided by that new exponent. And this is going to be from R naught to R3, or sorry, RE. Let's bring out this negative 1 out in front, which would cancel out with this negative 1. And we'll have G, M sub M, M sub E. Now this is just going to be 1 over R, where we replace R with R sub E, minus 1 over R, where we replace R with R naught. And this is going to be our final answer. We have it in terms of G, M sub M, M sub E, RE, and R naught. Just to check, the work done by gravity should be positive since the meteor is going to the same direction as gravity's pushing it. This number is positive because this is positive. R of E is less than R naught. So this number is going to be bigger than this number, making this positive. This is a positive value. And at least our conditional check here is good enough.